Falsificationism. So far we have been trying to solve the demarcation problem, which is a seemingly simple question. What makes science special? What is the difference between science and other things? We have looked at and discarded two answers already. The most recent answer was inductivism. According to inductivism, science is special because it followed a very special method. But the supposed method proved very problematic. Indeed, the realization that inductivism doesn't work wasn't news to anyone. By the time Popper wrote his book Conjectures and Refutations, the inductivist approach had given way to verificationism, a new philosophy which claimed to draw the demarcation line between science and other things correctly this time. According to verificationism, a belief, opinion, or theory is scientific if and only if it is verifiable by the senses. Verificationism was an attempt to seat scientific knowledge on a firm empirical grounding, but part ways with the rigid and algorithmic methodology posed by inductivism. However, verificationism's failure is even more evident than inductivism's. Indeed, the notion of verifiability is incompatible with science. Consider the following statements which you would encounter in the most basic science textbooks. All electrons have negative charge. All planets have elliptical orbits. All mammals sexually reproduce. How can a scientist verify these statements by observing the world? Verifying these statements is simply impossible because to verify them, we must observe all electrons, all planets, all mammals. There are just too many of them. So, by the standard of verificationism, even these rudimentary parts of scientific knowledge aren't scientific. Austrian philosopher Karl Popper understood the shortcomings of inductivism and verificationism, and he decided to put forward what he saw as a better solution to the demarcation problem: falsificationism. According to falsificationism, the scientific method is based on not proving or verifying any belief as scientific knowledge, but on testing our beliefs with the intention of trying to prove them wrong. Popper noticed that some opinions, beliefs, and theories are falsified. They are refuted by observed facts. Take Harold Camping, the immensely influential televangelist who predicted that the world would end on May 21st, 2011. Since you are sitting here and listening to this meandering lecture, Harold Camping was wrong. The world did not end in May 21st, 2011. His prediction has been falsified. Popper also noticed that some opinions, beliefs, and theories can't even be proven false. They are unfalsifiable. Consider, for instance, the old-school Marxist types who see evidence of the impending collapse of capitalism everywhere, but refuse to give a specific date. I once ran into a person like this during a train ride. He spent the better part of an hour trying to convince me that communism was not only good, but also inevitable. I asked him what would change his mind, what would prove him wrong. He seemed puzzled by this question because his beloved communism was so perfect and his unshakable confidence in its eventual arrival was so true that he would never change his mind. He proudly announced, "Nothing can prove me wrong." Popper too encountered many falsified, or worse yet, unfalsifiable belief systems. According to Popper, what makes science special is its difference from such belief systems. For him, scientific opinions, beliefs, and theories are falsifiable, but not falsified. This is the view which we today call falsificationism. On falsificationism, science works through the method of conjectures and refutations. Scientists do, or at least should, come up with conjectures, which are falsifiable theories, and they should then try to refute those conjectures by observation and experiment. Once this theory is falsified, we should abandon it because it is no longer scientific. And perhaps the longer a theory survives our relentless falsification efforts, the more confident we can grow in its truth. This Popper called verisimilitude, or truth-likeness. Of course, not every belief that is presented as scientific is falsifiable. In some cases, an unfalsifiable, unscientific opinion, belief, or theory is presented as if it is scientific, which we should refer to as pseudoscience. Pseudoscience, by the way, means fake science. For some reason, philosophers like pretentious Latin phrases. So, how do we spot examples of pseudoscience? Let's look at an example: Adlerian psychology. According to Adlerian psychology, all human behavior can be explained with a single principle: the desire to establish one's superiority over others. Imagine that a kid is drowning in a lake. A man sitting near the lake sees this and jumps in and saves the kid. Why did the man save the kid? How do we account for this behavior? Adler says because the man wanted to show his superior morals to the society by risking his own life to save a stranger. Now suppose that the man sees the kid, shrugs his shoulders, and lets the kid drown. Why did he do that? Adler says because the man wanted to show his superior ego that transcends the society's most sacred norms and taboos by letting a kid drown. So Adler is right. Come what may, there is nothing the man can do to prove Adler wrong. Like my fellow passenger on the train, Adler too has an unfalsifiable theory. Now compare that to a scientific theory, like Einstein's theory of relativity. According to this theory, massive objects such as stars bend the space itself. This would bend otherwise straight lines such as the path light rays follow. If, for instance, starlight passes near a very massive object, it would be bent by that object's influence on space. Of course, we don't usually notice this because the only thing massive enough in the solar system is our own sun. What's more, during the day when the sun is around, all starlight passing near the sun is drowned out by the immense brightness of the sun. So even if the sun bends the space, we can see its effects on starlight. Except, of course, during a total solar eclipse, which would momentarily dim the sun's brightness just enough that the stars in the same area of the sky would become visible. This gives us an opportunity to test Einstein's theory. If he is right, the apparent positions of the stars near the sun should shift slightly during the solar eclipse. If they don't, Einstein's theory is wrong. Of course, someone named Sir Arthur Eddington did this experiment, and the apparent positions of the nearby stars were shifted just as Einstein's theory predicted. But Popper's point for bringing this up as an example is not that Einstein's theory has been proven right. His point rather is that he could have been proven wrong, but he wasn't. Theories like Einstein's take risks. They could be proven wrong by observation. They are falsifiable. But theories like Adler's aren't falsifiable. There is no possible test, observation, or experiment that can ever contradict Adler's theory. No matter what someone does or doesn't, it always perfectly fits the theory. And that's why, at least for falsificationists like Popper, Einstein is a true scientist, whereas Adler is an imposter. Another remarkable aspect of falsificationism is how it analyzes the methodology of science. As you would recall, inductivists think that the scientific method is primarily inductive. A scientist starts from a number of observation statements and arrives at a generalization, which is usually a scientific law or theory. In this case, let's call this generalization the Swan theory, or TST for short. The scientific method, according to falsificationism, is very different. Scientists don't start with observation statements and arrive at generalizations. They instead start with a theory to test by extracting a prediction from that theory. Then they make observations and conduct experiments. The goal of these is to prove that the theory's prediction is false. If they manage to find a false prediction, then they can reject the tested theory as false. As you might have noticed, the inference on the right is deductive. So according to falsificationism, science doesn't rely on induction. This is not trivial. As you might remember, one of the problems with inductivism is that it leads to the problem of induction. According to inductivism, all science is premised on the assumption that the future will resemble the past. What we haven't observed yet will be like what we have observed already. If we are truly impartial observers of nature, which is something inductivism says we must be, then we cannot justify this assumption. But falsificationists like Popper claim that the scientific method doesn't use induction at all. For them, all science is deductive, so the problem of induction is solved by way of completely bypassing it. Falsificationism also does much better than verificationism. Again, consider the statement, all electrons have negative charge. By the current estimate, there are 10 to the power 80 electrons in the observable universe. That is 1 followed by 80 zeros. How do we examine each and every one of these electrons and verify that they all have a negative charge? This is simply impossible. So according to verificationism, we must declare the statement unscientific. What is worse, we would have to declare every statement like that unscientific. If we accept verificationism, there won't be a science left there to demarcate. But falsificationism deals with cases like this very easily. The statement, all electrons have negative charge, is very easy to falsify. Just find one electron that doesn't have a negative charge and you are done. The keen-eyed among you might have noticed that a falsification attempt can go in two ways. It can succeed in the sense that the recalcitrant evidence can be found and the theory can be rejected by way of falsification, or it could fail. The theory's prediction could turn out to be true. What should we do, according to falsificationism, if this keeps happening? Let's look at the example of the theory of relativity again. The theory makes a bunch of predictions. These are observation statements ranging from O1 to ON. If the theory is true, all these observation statements should be true. The scientists go out and make a bunch of observations to test the theory, hoping that they would prove Einstein wrong. But unfortunately for them, or fortunately for Einstein, all his predictions turn out to be true. No recalcitrant evidence can be found. What should scientists do then? Should they declare that the theory has been proven as true? This would be actually a logical mistake. Here's why. Take the successful falsification attempt where recalcitrant evidence is found. The theory made a false prediction, and we caught it. And compare that to the unsuccessful falsification attempt. The theory made a true prediction. You cannot infer the theory is true from the truth of its prediction. Indeed, doing so would be an example of a fallacy, which logicians call the fallacy of affirming the consequent. In contrast, you can infer that the theory is false from the falsehood of its predictions. That would be a deductively valid inference, unlike inferring the truth of the theory from the truth of its premises. This is why, according to falsificationism, we can disprove our theories easily. If one prediction turns out false, the theory is false. However, we can never confirm any theory conclusively. Of course, some theories, such as Einstein's theory of relativity or quantum theory, the theory of evolution, survive many elaborate falsification attempts. When this happens, falsifications conclude that the theory most likely has verisimilitude. Its truth content must outweigh its falsehood content. The technically oriented among you might be interested in looking deeper into the concept of verisimilitude, and in particular how it is absolutely unworkable. I left some useful information for those of you. But there are advantages to falsificationism. For one thing, it is simpler than inductivism. Scientists do only one thing. They try to disprove theories, yet, unlike in verificationism, simplicity doesn't come at the cost of rejecting almost all scientific knowledge as unscientific. Falsificationism also avoids the problem of induction completely. Falsificationism is also attractive as a diagnosis of dogmatic thinking. When you read conjectures and refutations, you know exactly what went wrong with the communist on the train, and many people like him. They got stuck in a belief system which doesn't let them out. Furthermore, falsificationism can provide some practical guidance in spotting scams that are presented as if they are backed up by science. When you run into a friend who bought a $900 alkaline water machine or swears by the truth of their chiropractor, you can easily spot them as victims of pseudoscientific scams. Finally, falsificationism is rather popular among scientists themselves, especially physicists. This prevents an odd situation where our opinions of what science is like doesn't match what scientists think it is like. But there are also problems. First, falsificationists recommend that we give up on our theories a bit too easily. Indeed, if we were to listen to their advice, we should abandon a theory as soon as we discover one false prediction made by that theory. To see why that's a bad idea, let's look at a historical example. Astronomer William Herschel discovered Uranus, which is the seventh planet, in 1781. There was something odd about Uranus's orbit, though. It was noticeably different from what Newton's theory of universal gravitation predicted. By the logic of falsificationism, we must reject Newton's theory now, because it predicts the orbit would be one way, but it is observed to be another way. Therefore, the theory must be false. But the scientists of the time, including Herschel himself, remained loyal to Newton's theory despite the fact that it made a false prediction about the new planet's orbit. If you ask someone like Popper, this is a terrible idea, because now these people aren't acting like scientists anymore. They say that they are scientists, but because of their dogmatic attachment to Newton's falsified theory, they are actually pseudoscientists. However, history teaches an entirely different lesson. In fact, the loyalty of those supposedly pseudoscientists paid off. They thought that an unseen planet must be tugging on Uranus, which is why the orbit wasn't as initially predicted. So they used Newton's theory to calculate precisely where this unseen planet would be and looked for it. Lo and behold, there it was, the eighth planet, Neptune. Crucially, had they agreed with falsificationism, they wouldn't have discovered Neptune, and instead they would have prematurely given up on a very powerful theory. The lesson to draw here is anti-falsificationist. In some cases, it is rational to hold on to a theory in the face of recalcitrant evidence. Next, there is the problem that falsificationism oversimplifies the logic of science. According to falsificationism, testing a theory such as Newton's theory of universal gravitation is rather simple. You extract a prediction from the theory and try to prove the theory false by observing that the prediction is false. But this is a bit oversimplistic. Remember, if scientists followed this logic, they would have perhaps never discovered Neptune. What is closer to the truth is that you extract a prediction not only from Newton's theory, but also from the assumption that there is no unseen planet tugging on Uranus. But even that is oversimplistic. Indeed, there are many assumptions we have to combine with the theory to test it, such as the assumption that the telescope is working properly, you ran the numbers correctly, there is no atmospheric phenomena skewing your observations, and so on. We will revisit this point next time, but the brief lesson to digest here is no theory can be tested in isolation and be refuted by one failed prediction. Finally, falsificationism also seems to ignore important differences between predictions. According to falsificationism, a successful prediction means only one thing: the theory has survived to fight just another day. But some true predictions are more valuable than others for scientific progress. Correctly predicting the orbit of a previously unseen planet like Neptune is an amazing achievement. Correctly predicting that the apple will eventually fall from the tree if no one picks it is not an amazing achievement. But both of them are among the true predictions of Newton's theory. Shouldn't we be more excited about the former rather than the latter? In other words, in science, some true predictions are more valuable than others because they pave the way to new discoveries. But falsificationism doesn't care much about true predictions. It focuses almost exclusively on the attempts to falsify a theory. To recap, the demarcation problem is a simple question. What makes science special? What is the difference between science and other things? Today we looked at a third answer, which is falsificationism. Falsificationism is the view that what makes science special is its falsifiability. Only falsifiable opinions, beliefs, and theories can be scientific. Falsificationism has advantages, such as bypassing the problem of induction, so it looks like we might be approaching a better answer. However, we are not there yet, as we noticed some serious problems with falsificationism. This is of course what Feyerabend said. He said falsificationism is unworkable as a solution to the demarcation problem. Which brings me to the end of this lecture. Send me an email if you have any questions. Thank you for your patience, and I'll catch you next time.